Welcome to ECE 165. This is lecture 4, where today we're going to be discussing MOS capacitance, how to use MOS capacitance for the calculation of delay in CMOS circuits, and we'll get a little bit into the design of how we actually size transistors in order to get the functionality and speed that we're looking for out of our circuits. So let's go ahead and get started. We're going to start today's lecture by talking about MOS parasitic capacitance. Okay, so this is an important topic. It's important for analog design, as you may have studied in your analog design classes. It also turns out to be very important for digital design as well. Okay, so let's go ahead and get started by drawing a cross-sectional diagram of a MOSFET transistor. So it might look something like this. This is the gate area here. Underneath the gate, we have some oxide. Conventionally, this has been silicon dioxide. Could be something else in a slightly more modern CMOS process. And then underneath all of this, we have our silicon substrate. And within this substrate, we have some doped regions that create the source and the drain. Now, between all of these areas, and sorry, just to label, this is the gate, this is the source, this is the drain, and this is the P substrate. Okay. Now, just to be clear, there is capacitance that exists across all of these terminals here. So this would be what we call CGS. This is CGD. We have capacitance between the gate and directly in the substrate. This is CGD. And then we also have capacitance between the doped region and the substrate. This is CSB. And capacitance between this doped region and the substrate, and that's CDB. Okay, so when we go ahead and draw our transistor circuit diagram, in digital we draw it something like this. And let's just say that the bulk comes out here. This is the gate, the drain, the source, and the bulk. And basically what this means is we effectively have capacitance between every single terminal here. So between CGD, CGS, we also have capacitance between the gate and the bulk, that's CGB, and then we have capacitance CSB and CDB. Okay, so unfortunately, this ends up slowing our digital circuits down. So as digital circuit designers, we have to be very careful and be aware of all of these various types of capacitance. Now, all of these components are nonlinear. And subsequently depend on the region of operation of the transistor. So the amount of capacitance depends on the region of operation of the transistor. This means that simulations are required in order to get accurate understanding of what that capacitance is. Now, with that being said, we will present some intuition, and rules of thumb. Okay, and let's start that perhaps on the next slide. So let's start with CG. Okay, so let's first define C naught as equal to Cox times W times L. So this is obviously something that we've seen a lot before. Cox in this case is equal to epsilon ox over T ox, which is the parallel plate capacitance between the gate and the bulk. Okay, So with that definition, let's go ahead and construct a table that will describe how much capacitance we're going to have in each of the three regions of operation. Okay, so let's construct the table in the following manner. We have the region of operation up here. So we have the cutoff regime, which we will study and understand that it's actually not cutoff, it's actually subthreshold. We have the linear regime and the saturation regime of the transistor. And we're interested in CGB, CGS, CGD, and CG, basically total. Okay. Now, in the cutoff regime, we don't have a strongly developed channel, and therefore we don't have a lot of parasitic capacitance between the gate and the source and the gate and the drain. And rather, pretty much all the capacitance is between the gate and the bulk. I'm going to say less than or equal to, it's slightly more complicated than this, but this is a good first order approximation. And so our total capacitance seen by the gate is basically just C naught. Okay. Now in the linear region, we've started to invert that channel. Therefore, the channel is conductive, and we effectively lose this capacitance between the gate and the bulk, and instead spread it between the gate and the source and the gate and the drain, just because of that conducting channel. Okay, so we say that we just sum those two up, and the total capacitance as seen by the gate is also C naught. Now, something similar happens in saturation. In saturation, we have essentially no capacitance between the gate and the bulk, and instead that capacitance goes mostly to the gate to source capacitance, and we're going to say approximately zero capacitance is from gate to drain. So the total capacitance is 2/3 C naught. Okay, so the question is why? And the answer is because of channel pinch off. Okay, so this is an effect when we get into the saturation regime, where the width of the channel basically starts to pinch off away from the drain, and that effectively causes most of the conductance to be realized between the gate and the source, and therefore that's where we see the large majority of the capacitance there. Okay, so from this perspective, we say that, and again, this is not totally accurate. This is a good first order approximation, but we effectively say that the capacitance is 2/3 C naught in saturation. Okay, so what we've described so far is what we call parasitic capacitance, or in other words, capacitance that exists in the device, even if the device were perfectly fabricated. Now, there's also something called overlap capacitance, which occurs due to fabrication imperfections. Okay, and so what we mean here is that the gate overlaps the source and drain regions by a length called LOV. Okay, and just to be explicit here, if we quickly just redraw that Mosfet, if you notice in that first drawing, I intentionally put these doped areas here a little bit into the channel, and that's because what ends up happening is you get this little area here called the overlap area. Okay, and this is typically required in a manufacturing process because you want to make sure that the doped area is right next to the channel, and ideally LOV will be 0. You definitely don't want LOV, at least in this definition, to be negative. That is, the doped region is away from underneath the gate. So you definitely don't want that, and so manufacturers tend to err on the side of having a little bit of overlap just to make sure that the transistor is fabricated correctly. And so in this case, we say CGS, overlap is equal to COX W times L overlap, which we call which is also equal to CGD, OV, provided provided there is no variation between the source and the drain regions. Okay, so given that, we can say that let's get a C there, CGS total is equal to CGS plus CGS overlap. And you'll notice I'm being a little sloppy in the terms of in the use of uppercase versus lowercase variables here. In analog design, this means something. In digital design, we can get away with being a little bit more sloppy, although I will try and stay a little bit more consistent. So I do want to take a side note, because it's something that I often ask senior undergraduate students, and it's surprising how many don't have the answer to this, is how do you measure capacitance? Okay, so let's say I give you physically a transistor and I say, tell me how much capacitance this transistor has. Or let's say, perhaps more realistically, I give you a transistor model, and for whatever reason the model netlist is encrypted or something like this. You can't look it up, and so you need to figure out how to simulate this device and figure out how much capacitance there is. Okay, so we don't have necessarily just a capacitance meter or a capacitance measure function in HSPICE, for example, and so you typically have to construct your own ways to measure capacitance. So one solution to do this, for example, and there's many ways to do this, of course, is to create a current source and tie that to the capacitor. Okay, now because V is equal to 1 over C integral I dt, provided that's a constant current source, then what you're going to find is that the voltage on the capacitor is going to ramp up, and so you can just basically measure the amount of time it takes to hit a certain voltage, or the voltage it hits after a certain amount of time, and that will, through that integral, allow you to compute that capacitance. Another possible solution, number 2, and again, there's many different ways to do this, is if you can create an AC voltage source, have some known impedance, and then connect that to your capacitor. This creates a voltage divider at AC that you can use to compute the effective capacitance. Okay, so there's some more capacitance we have to concern ourselves with. The next one is diffusion capacitance. All right. Now in this case, I'm going to do my best to attempt to draw a three-dimensional transistor here. Okay, so bear with me. So here is the gate material here. I'm going to draw the transistor going in this direction here. All right, so that's the gate. And now I'm going to draw the source region. Okay, so the source region is going to look something like this. I'm going to, normally we've been drawing it as kind of this half oval shape. In this case, I'm going to draw it as more of a box just to make the modeling easier. This is where our channel would happen. So this is a decent description here. Now, to be fair, this is supposed to be a three-dimensional model, so we should be seeing the kind of internal area of this device over here. Okay, so let me label a few dimensions here. I'm going to say this dimension here is called D. This dimension over here is called W. This is the width of the transistor. The length, of course, is this area over here, all the way to the other side of that transistor. And then I'm going to call the height of this doped area T. Now looking in from the bottom, this is what we're going to call the bottom plate over here. Okay, so that's, and just to be clear, this is the channel over here. So that's not a terrible drawing. Actually, I'm fairly happy with that. Okay, so let's label a few things. So there's junction capacitance. We'll call it CJBS. And this is the capacitance per unit area of the bottom plate. And this is in units of femtofarads per square micron. Okay, so this is the area of what you'd call the bottom plate region here, right? So you measure the bottom plate, and the area of the bottom plate, which is in this case just W times D, and you use that to compute the amount of CJBS. Okay, and then there is CJBS SWA, and this is the capacitance per unit length of the sidewalls. Okay, and the sidewalls are nothing more than the front, the side, and the back of this area. So we've already taken the bottom plate. There's no capacitance on the top plate. Now we have to take the whole sidewalls here. Okay, and this is in units of femtofarads per micron because we normalize it to unit length. Okay, so we can say that in this case CSB is equal to D times W times CJBS. Okay, so CJBS is the capacitance per unit area of the bottom plate. We multiply by the area of the bottom plate, which is D times W. And then we have to add the sidewall capacitance. So we multiply by the perimeter around the sidewall. So that's 2D plus W times CJBS, comma, SWA for sidewall. Okay, so this describes the total amount of diffusion capacitance in our design. Now, this is only scratching the surface. If you want to learn more about this, it's described in section 2.3.3. All right, so now that we have a pretty good idea of where capacitance is coming from in our circuits, what I'd like to do now is let's go ahead and calculate the capacitance seen by a real circuit. So let's do an example. For example, what is the capacitance seen by a loaded inverter? Okay, so first of all, what do we mean by loaded inverter? Well, it's rather simple. So we have our input voltage here. This is going into one inverter. Just draw the inverter here, NMOS and PMOS together. Okay, this is our one inverter. And then this is going to be loaded by a second inverter of the same size. Okay, so there's our second inverter. This is technically our output voltage. Now Vout should be equal to Vin, albeit with respect to some delay between those two nodes. Now, because we're dealing with real MOSFETs here, we now have to deal with the parasitic capacitance that we might see all over the various MOSFETs. I'll put my solder balls here to make things extra clear. Okay, and so what do I mean by that? Well, all of these transistors have parasitic capacitance everywhere. And what we'd like to do is we'd like to represent that parasitic capacitance by some one overall load capacitance. We'll call this CL. And this is on node Vx here. Okay, so we'd like to understand what that overall effective capacitance on this node connecting these two inverters is. So in order to do that, we have to go ahead and calculate the parasitic capacitance that's connected to that node. Now it turns out there's lots. Okay, so we have, for this transistor, we have CdB, comma N for NMOS. If we have that for the NMOS, then we of course also have that for the PMOS. This is CdB PMOS. Now you'll note I'm connecting that other side of the capacitance to VDD in this symbol, For the purposes of parasitic capacitance calculations, it doesn't really matter. You could connect it to ground. It's basically acting as an AC ground because we're using capacitance for the purposes of effectively small signal calculations, although technically in digital circuits these are actually large signal phenomena that we're dealing with, but we do make some small signal approximations, which we'll get into momentarily. So we have our CDBs. We also have, and those of you who do analog circuit design will groan when we talk about CGD, N for the NMOS transistor, and we have the same thing for our PMOS transistor, CGD, P. These CGDs always tend to introduce all sorts of problems in analog circuits. In digital circuits, they also introduce problems, but we'll figure out how to deal with them. Now, technically, we also have some capacitance between the source and the bulk, CSB, but we can safely ignore these because, well, they're grounded on both sides, and so therefore they don't contribute any losses or they don't operate in the circuit. Okay, so we can ignore these. Now, of course, we have these same capacitors on the subsequent inverter as well. Okay, so first of all, we can perhaps start writing down the answer. CL is going to be equal to what? Well, we definitely have the CGDs of the first transistor that are coming into play here, and we have the CDBs. Okay, so let's go ahead and add those CDBs first. Okay, so I'm going to call that CDB, N plus CDB, P. Okay, so those are easy. Now, what about these CGD terms? So it turns out it's a little bit trickier than perhaps we would originally think. And to understand that, let me draw a timing diagram. Okay, so this is our V-in signal, and let's say it goes from 0 to VDD. It has some finite rise time and then some finite fall time. Okay, so the amplitude of the signal here is VDD. Now, if we then go ahead and look at Vx, okay, Vx is the inverted version of Vin. So it starts high, and then after some delay, it goes down with some fall time, and then it goes up here. Okay, the swing on this signal is also equal to VDD. Now, if you'll recall, what ends up happening here is CDB, either N or P, this happens to both, charges from 0 to VDD, or vice versa. Okay, so in this particular example, Vin is going from 0 to VDD, so therefore Vx is going from VDD to 0. So CDBN and CDBP both were originally charged to VDD, and now they've been discharged to 0 during this first transition here. Now CGD, either N or P, charges from, well, let's just think about this. Vx currently is at VDD before that first transition, and Vn is at 0. So we have plus VDD across the capacitor, and then after the transition, the Vx terminal of CGD is now at 0, and the Vin terminal is now at VDD. So it charges from plus VDD to minus VDD, or vice versa. Okay, so this actually starts to imply something that's perhaps familiar to those of you who've done your analog classes. We have a capacitor whose voltage on both sides is changing, and it's changing in the opposite direction. So this results in, yes, the Miller effect. Okay, so In analog circuits, what we typically do is we take that capacitance and represent it by a single capacitor whose size or whose value is increased by a factor of 1 plus A, where the A is the gain of the amplifier. Now in this case, we're dealing more with large signal behavior, so it's a little bit more tricky to do this. So what we typically do in digital circuits is we replace this CGD capacitance with a capacitor to ground, but 2x larger. Okay, so basically we're saying because of the Miller effect, we basically see double the amount of capacitance on that node simply because it's charging over double the amount of voltage. So what we say then is we have 2 CGD total N, I'm using total because we should also include any overlap capacitance that might exist here, plus 2 times CGD total P. Okay, so are we done here? Well, not quite. That's all the parasitic capacitance of that first inverter. We also have parasitic capacitance from that second inverter. So we have CGS total 2N. In this case, we do have to include CGS because it's connected to the VX node, plus CGD total 2N. And the 2 just represents it's the second stage. Okay, plus, actually let me just draw this down here, plus CGS tote 2P plus CGD tote 2P. Now, you might be saying here, well, hold on a second. We used a factor of 2 due to the Miller effect for the CGDs of that first inverter, and now we're not including that factor of 2 for the CGDs of that second inverter. So I'm going to say that there are, actually let me take that as a note up here, no 2s here, since we assume the second gate doesn't switch until after the 50% TPD of the first gate. Okay, so basically what we're saying here is when the first gate is transitioning, we are trying to calculate the effective capacitance on the output of that first gate. And when it's transitioning, we have a change in voltage at the input and a corresponding change of voltage right at the output. And didn't really line these curves up here very well, but they're trying to basically be switching at the same time. Okay, of course after a propagation delay. Now that second gate, when we are calculating the capacitance at node Vx, is not going to start to transition until after Vx has reached that 50% point, at which point we don't care as much what its capacitance is. Okay, this is a little hand wavy. Of course, if we wanted to do a very detailed calculation, the only real way to do this is with basically a SPICE model where you can kind of figure out what the dynamically varying capacitance is and apply the Miller effect in the appropriate way and so on. But from a first order rule of thumb perspective, this is perhaps the best way to account for all the capacitance. And so we're going to use this convention for the purposes of calculation in this class when we look at homeworks and exams and so on. So please do keep that in mind. We take the Miller effect into account for the gate preceding the node in question, but we don't take the Miller effect into account for the gate following the node in question. Okay, so that was a very detailed calculation, and frankly, it's a reasonable model for us to be using in this class, but why the heck do we even care? Why do we care about calculating the capacitance? Capacitance will be there, it's annoying, but who cares? Okay, so I want to make a specific or rather explicit point about the implication of capacitance. Why do we as digital designers even care? We're not talking about bandwidth of an analog circuit or something like this. Why do we care about capacitance? So let's dive into this. It turns out it's actually rather important. So given that transistors output finite current So for example, ID sat, we have a NMOS or PMOS transistor that is saturated. It can't push more current through than the on current of the device. A finite load capacitance means that transitioning or that transitions from VDD to ground and vice versa require finite time. So the fact that there is capacitance there means that intrinsically limits the performance of our circuit. So if you recall, the voltage seen over a capacitor is 1 over C, the integral from 0 to tau of I of t dt. Okay, so the speed of CMOS is thus limited by capacitance. And of course, charging current as well. So if we can design a better transistor with better charging current isocapacitance, that means for the same amount of capacitance, then we should be able to get better performance. Now, there's a bunch of different ways we can use to make models, to predict speed, and so on. We're going to discuss a bunch in this class, but we often idealize, just for simplicity, charging in digital CMOS circuits using an equivalent resistance. Okay, so it turns out that this is actually quite a bit more complicated in reality, but let's just go through a quick example for an inverter. Okay, so again, we have our inverter. Looks something like this. There's solder marks there to make sure everything's clear. So we can go ahead and represent this circuit as the following simplified circuit. So we represent a transistor with a switch and a resistor. Okay, so something like this. All right, so this is V out. This is our effective load capacitance from the intrinsic capacitance of the transistors, as well as whatever load we have out there. Okay, so let's just imagine, actually, sorry, let me label this R on for N and R on for P. Okay, let's just for a moment imagine that this NMOS transistor turns on. Prior to this, the PMOS transistor was on, and so therefore V out had been charged to VDD. And at some instance in time, let's say t equals 0, the NMOS transistor turns on and the PMOS transistor turns off. Okay, so let's just plot what's going to happen to this voltage. Okay, so I'm plotting V out of t versus t. So we said that at t equals 0, and perhaps for all time before that, we had V out was equal to VDD because that PMOS transistor was turned on. Okay, but as soon as the PMOS transistor turns off, we can say that that switch opens. This is just a model, but let's just say the switch opens. And at that same instance in time, the NMOS transistor turns on. Okay, so the NMOS transistor turns on. We are representing the on resistance of the NMOS as an effective resistor, R on, N. Now, we know that in actuality, the resistance isn't actually fixed, because as the voltage of that NMOS transistor changes, the mode of operation of the transistor will change, and therefore its resistance will change. But to first order, we'll say it's approximately the same throughout the switching period. And if it truly is modeled by a resistor, then basically what we get is an exponential delay model, something like this. Okay, and specifically, the function is VDD times 1 minus e to the minus t over R on, N times CL. Okay, it's a decaying exponential function. So basically what's happening is the capacitor was charged, and then once that NMOS transistor turns on, we have some current that flows through it that discharges that capacitor all the way to 0. Now again, we could have modeled our transistor as a current source. That's also a valid model. In reality, that current source also changes as the voltages across the transistor change and as the mode of operation or the region of operation of that transistor changes. But this is, I think, a reasonably simple model that we are going to use throughout the rest of this course. Okay, so this brings us nicely into our next topic, which is a topic on delay. All right, so this is a new section, so I'm going to double box this, and this is related to chapters 4, or chapter 4 in West and Harris. Okay, so let's first start with some definitions. Okay, and these definitions are going to be important, so let's go through them relatively slowly to make sure that we're all on the same page. So what I'm going to draw is a timing diagram. I'm going to draw an input waveform. It's going to start at 0. It's going to make its way up to logic 1. It's going to stay at logic 1 for a little while, and then it's going to make its way back down to, well, let's draw that a little bit more accurately, down to 0. I don't want to have it drawn all the way on the axis because then you can't see what's going on. Okay, so at the top here we have VDD. The midpoint here we're going to say is VDD over 2. Okay, so that's the input waveform. Let's go ahead and look at the equivalent output waveform. Let's say it's going through an inverter. So if it's going through an inverter, the waveform is going to be starting high. After a propagation delay, it's going to go low. After another propagation delay, it's going to go high again, and so on. Okay, so again, this is VDD, and sorry, I should label these. This is V in and V out. This is VDD. We'll draw a line through the middle here, and this is VDD by 2. Okay, so the important points, the most important timing definition here is the distance in time between these two waveforms to cross VDD by 2. Okay, so we call this the propagation delay. Specifically, this one is the propagation delay for the falling edge of the output, and this is the propagation delay for the rising edge, TPR. Okay. Now, the reason we care about propagation delay and not so much for, you might think of delay as like rise time or fall time or something like this, and we can use different definitions for what rise and fall time might mean. Is it the rise time 0% or 10% of the signal to 90% or 20 to 80%? Something like this. Those are important and they do matter in certain circuits, but as we'll find in digital design, it turns out that it's the propagation delay. How long does it take an edge to propagate through a gate? That becomes the very important metric that we really have to concern ourselves with. So we say that the propagation delay of the falling edge, some people will also call this the propagation going from high to low at the output. Similarly, the propagation delay of the rising edge, some people call this the propagation delay from low to high. And if someone just says the propagation delay without specifying if it's the rising or the falling, then the definition is typically we just take the average of the two. Just TPF plus TPR divided by 2. So this is propagation delay. Okay, so before moving on into analysis, I want to introduce a class convention. Things can get very complicated unless we simplify our lives a little bit. So I'm going to introduce this class convention, and this will be used for lectures and homeworks only. I will specify on exams if the class convention is appropriate or not. Okay, and I suppose that's true in homeworks as well. And in labs, the class convention will most likely not be true. Okay, because we're using realistic transistor models here. But for the class convention, to keep things very simple and allow us to do simple analysis for equal drive strength, what we want to do is set W over L of the PMOS transistor to be equal to 2 times W over L of the NMOS transistor. In other words, we're saying that the PMOS transistor is half as strong for the same size as the NMOS transistor, and in order to have equivalent delay through the circuit, we need to size our PMOS transistor to be double the size of the NMOS transistor to get the same performance. Okay, so what that means is if our NMOS transistor is a normalized size of 1, then our PMOS transistor has to be a normalized size of 2 in order to have equal drive strength. And by equal drive strength, just to elaborate on what this means, this is to have symmetric voltage transfer curve around VDD by 2, or in other words, TPR is equal to TPF. The rise time is equal to the fall time. Okay. Now, let's imagine we're doing this in our 45 nanometer technology. Then what we'd say here is if we implemented an NMOS of size 1, what we really mean by that is something that's 100 nanometer over 45 nanometer or 50 nanometer, depending on how the PDK does it. And the PMOS of size 2, that means it has in order for it to be size 2, it would have a width of 200 nanometer and a length of 45 nanometer. Okay, so if we're assuming that we're using minimum length transistors, which in digital design is almost always the case, not necessarily 100% of the time, but 99.9% of the time, an NMOS with width X times W min will have, let's just call this R new, comma N for the NMOS. It will have the minimum resistance for an NMOS divided by X. Okay. For PMOS, we say that if it has size X, then R new of this new size PMOS over the minimum one is going to be 2 R min NMOS divided by X. It's not MNOS. Let's get that right. NMOS. Okay. So for both NMOS and PMOS, capacitance scales linearly. And what I mean by that is the gate capacitance, the drain capacitance, etc., is just X times the capacitance of, say, the minimum size transistor. So I'd like to be as explicit as possible when we're talking about this class convention and help everybody in the class be able to more easily understand and quickly derive an equivalent circuit model for the purposes of computing delay. So with that, I'd like to introduce some useful constructs. It's nothing that we haven't already covered in the prior slide here, but I want to just be very explicit and go a little slow here to make sure that everybody's on the same page. So let's talk about an let's start over here. An arbitrarily sized NMOS transistor. Okay, so we want an NMOS transistor. Let's just draw it hanging out in the ether here. We have gate, drain, and source. And let's say this NMOS transistor is of size K. Okay, so I'm going to say that this circuit can be represented by the following circuit. We have gate. We have some parasitic capacitance here that activates our switch. This is our switch model. Goes to our source. This has some capacitance on the source side. We have some resistance on the drain side, and we also have some capacitance on the drain side. Okay, so we're going to say that if this NMOS transistor is of size K, then we have Kc capacitance on each of the nodes here, where C is the nominal capacitance, and the resistance is of size R over K. Okay, so let's just write this down. So R, let's say R new, comma N, is equal to R min, comma N, divided by K. Okay, so if we think of a minimum size transistor of having a capacitance, or sorry, a resistance of R min, then if we have a K size transistor, NMOS transistor, then it would be, the resistance would be R min over K. So it's an inverse, it's a reciprocal relationship, which makes sense. The bigger the transistor is, the smaller the resistance ought to be. Okay, so likewise for capacitance, C new, comma N is equal to K times C min. So if a minimum size transistor is of size, has a capacitance C min, then a K size transistor will have a new capacitance of K times C min. Okay, and just to get min out of the picture, on the picture of the right, I just said C and R, understanding that C is a unit size capacitor and R is a unit size resistor. Now we can do the same thing for an arbitrarily sized PMOS transistor. Okay, this time, let me draw actually this time I'm going to write down the formulas first. R new, comma P. Now remember, per our class sizing convention, a PMOS transistor has double the amount of resistance as an NMOS transistor. So it's 2 times R min, comma N. All right, so let me put a little asterisk here. Yes, that's not a typo. 2 R min N divided by K. And the capacitance C new P is just equal to K times C min. The capacitor doesn't change. Okay, so again, what this means is that a PMOS transistor has by nominally twice the amount of resistance as an NMOS transistor, but the 1 over K relationship remains. Okay, so if we have our PMOS transistor here, this is the gate, source, and the drain, and it is of size K, then we can say that this can be represented by the following circuit model. We have the gate that goes onto some capacitance. This capacitance triggers a switch. The switch has some resistance attached to the source with some capacitance, and the drain, of course, also has some capacitance. Okay, so let's just fill this in. These guys are Kc, 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 exactly the same as for the NMOS case. But now, per our class sizing convention, the amount of resistance is 2R over K. So again, the reciprocal relationship with the size of the device is still there. If you build a bigger device, the resistance ought to be smaller. But per our class sizing convention, the PMOS transistor has double the amount of resistance nominally relative to the NMOS transistor. So with these two useful constructs, you should be able to go into any circuit we show to you, and assuming the class sizing convention holds, go ahead and replace each transistor with the circuit model and then figure out what kind of delays are going on in our circuits. So what I'd like to do now is, now that we have those useful constructs in place and we understand the class sizing convention, let's go through a simple example. Let's, using this model, estimate TPDF, the propagational delay of the falling edge, of a minimum sized inverter designed with a symmetric voltage transfer curve with a fan out of 1. And what that basically means is just it's loaded by a similar inverter. Okay, so let's just go ahead and draw the kind of top level picture of what we're dealing with here. So we have two inverters. Now I'm going to label the insides of the inverters with a number here. I'm going to label them as 3. Okay, this refers to the total input capacitance. Okay, so looking into the gate of this inverter, we have 3C of input capacitance. All right, that's going to come, we're going to do things like that all the time for the duration of this class. Now we're specifically interested in figuring out the V in to V out falling edge propagation delay. Okay, so let's just go ahead and take a look at what's inside one of these inverters. Well, it's just, you know, a classic inverter, PMOS and NMOS on top of each other. How do we get a size of 3 here? Well, the NMOS is size 1 because it's minimum size, and for a symmetric voltage transfer curve, according to the class sizing convention, the PMOS needs to be of size 2. 2 plus 1 is 3. Should be straightforward. So let's go ahead now and represent this circuit with our useful constructs. Okay, so let's represent our PMOS transistor here. We have our resistance, we have our switch, we have some capacitance here, we also have some capacitance here, although we'll find out that that doesn't matter too much. And then we have our NMOS transistor, we have some capacitance over here, we have a resistor, our switch, and then ground, and we also have some more capacitance over here. Okay, so first of all, let's go ahead and calculate the size of all these components. Well, we know these capacitors on that NMOS transistor are of size C. The capacitance on the PMOS transistor are of size 2C. The resistance on the NMOS transistor is size R. And remember, we've intentionally upsized that PMOS transistor by a factor of 2, so its resistance is actually just R. Okay, this is why it has a symmetric voltage transfer curve. Now, the other thing to note is that these capacitors here are not, you know, they're shorted, so we don't have to consider them. And then we also need to note that we are loading this inverter with a fan out of 1, which just means it has a replica circuit attached to the other side or to the output there, and so this has C and 2C worth of capacitance. All right, so this is our circuit model. So what happens when the pull-down network is active? Well, when the pull-down network is active, we basically have a circuit that looks something like this. We have some capacitance at the output. The total capacitance at the output is 3C plus 3C is equal to 6C of capacitance at the output. And the reason is because we have 3C of capacitance from our first inverter and an additional 3C of capacitance from our second inverter. And we have a resistance R here. So when that switch turns on for the pull-down network, we're going to have some current that discharges from the capacitor through that resistor. We can go ahead and plot what that looks like. It'll look just like what we plotted earlier. So we have V out versus T. We started at VDD, and then we had an exponential delay function. That's not totally exponential looking. Let me try that again. That's a little bit better. Okay, so let's mark down a few points here. So this is our time t equals 0. And what we're specifically interested in doing here is figuring out, we were at VDD, how long does it take us for us to get to VDD over 2? Okay, this time here is going to be equal to TPDF. This is our propagation delay on the falling edge. Now, as you'll recall, the formula here for this decaying exponential is VDD times 1 minus e to the minus t over, in this case, it's 6RC. So if you recall your formulas for decaying exponentials, you actually can just do this perhaps by memory or by inspection. We say TPDF is equal to 6RC times the natural log of 2. This is the time it takes to go from VDD to VDD over 2. Okay, so this is the final answer. Now, I will say that since R is empirical, that is, it's kind of a model. We usually have to measure or simulate it to get exactly what R looks like. Let's just go ahead. Let's lump log 2 into the R term. Okay, this way we don't have to carry around the R term. Then what we say is TPDF. Actually, let me write this to be consistent in green. TPDF is just equal to 6RC. Okay, that makes our life a little bit easier. We don't have to carry this log 2 around all over the place. Okay. So we've now computed the propagation delay for a falling edge. So what about TPDR, the propagation delay for the rising edge? So as you recall, for a rising edge, the pull-up network is active. The pull-down network has been disconnected. So we can model our circuit as follows. We have a resistance for our PMOS transistor, and our loaded capacitance is the same. We have 6C here. We have R's worth of resistance up here. And we say that instead of discharging the capacitor, we're now charging the capacitor from supply VDD. Okay, so we can say that TPDR is, well, according to the class sizing convention and what we showed earlier, is also equal to 6RC. In this case, the natural log of 2 is included in the delay calculation here. Okay, so I just wanted to explicitly show this because sometimes students get confused of, we're always connecting things to ground, we're always discharging things, but what happens in the opposite scenario when we're charging? Well, it looks the same basically, but you just have to make sure that you're taking the right resistors and capacitors into account. So I want to do one more question. What is TPDF for an unloaded inverter? Okay, so this is an inverter that has fan out of 0. There's nothing connected to it. It's just sitting there on its own in the ether, not connected to anything. Well, again, we can take out our effective circuit model using our useful constructs there and construct a model. And it's going to look just like the model we had before. In this case, we have R's worth of resistance, and now we only have 3C of capacitance. So in this case, TPDF is equal to 3RC. Now, it turns out that this term, 3RC, comes out a lot. Okay, so we're going to make a convention. Just something to keep around to, I guess, save us a little bit of writing. Engineers are lazy, saves us a little bit of writing. Tau is equal to 3RC, okay, which is equal to what we call the intrinsic delay of a unit sized inverter with symmetric voltage transfer curve. Okay, so we are going to make more use of this tau concept a little bit later on in the course, but for now what we'll say is that when we have a unloaded inverter, even if it's not driving anything, because it has its own intrinsic capacitance, it has its own internal delay, and that delay is given by 3RC. So given all of this, I want to ask a question. How does one design for speed? Okay, in digital circuits, we're typically interested in making our circuits as fast as possible. We'd rather have a processor that we can clock at 4 gigahertz than a processor we can clock at 2 gigahertz. So how do we do this? Well, the intrinsic delay is proportional to R and C. All right, so there's not many variables we can play with here. What can we do? Well, let's start with C. We can try and keep capacitance small. So how the heck do we do that? Well, we can keep our transistors very small. That's also good for transistor density and other reasons, but the main way that we do this is we shift to a faster process technology. So let's say we'll use 14 nanometer instead of 45 nanometer process. Now, we have to rely on the process folks to keep Moore's law, heading down, which may or may not continue to happen. So, as designers, we're only limited by whatever the process can give us, other than kind of keeping our design sizes rather small. And interestingly, actually, this poses an interesting optimization problem that we may encounter in perhaps in homework or something that basically says that maybe we don't want to optimize our circuits for symmetric voltage transfer curves in the pursuit of trying to achieve as fast of speed as possible. Now we can also have control over the R term. So we can keep R small by, well, how do we keep R small? By increasing the size of our transistors. Damn it. We just said we want to keep our transistors small to keep C small. So we can't just upsize our transistors. So let's keep R small by limiting self-loading. So I'm not going to say anything more than that other than see homework 2. You'll explore this trade-off in homework 2. Now the other powerful way to decrease R is to increase VDD. So how the heck does that increase R? Well, effectively reduces R by having a larger VGS, right? When we're dealing with logic, digital logic, our supply VDD sets the gate voltage of all of our gates that we're building. And so a larger VDD means a larger gate voltage, which means VGS will be larger, which means that we more strongly invert the channel, therefore its resistance will be lower, and so on and so forth. Okay, so this is good. Now it turns out process restrictions mean you can't just arbitrarily increase VDD, otherwise the transistors will start blowing up. In addition, we actually have some power consumption constraints that come along with increased VDDs. We'll talk about those later on in this course. So the short story here is there's no silver bullet, there's no free lunch. We as digital designers just have to do a very good job of making sure we understand our trade-offs very well to make the best decisions for the types of circuit that we are trying to build.